Privileged access is where small weaknesses can become major breaches. Attackers steal credentials, raise privileges, move across systems, and target sensitive data. In this module, we'll connect those attack patterns to stronger controls like least privilege and zero trust. We've already built the foundation: how identities prove who they are, how access is granted, and why privileged accounts matter. Now we'll look at how attackers exploit those same concepts through stolen credentials, privilege escalation, and lateral movement. That threat context will help explain why stronger access controls are necessary. Privileged access is attractive because it can turn one stolen credential into many options. Instead of breaking into each system separately, an attacker can use an admin account, service account, or cloud role to move quickly, change settings, disable defenses, and reach sensitive systems. That makes privilege a force multiplier. A small initial compromise can expand into control over identity systems, servers, databases, pipelines, or security tooling. When PAM controls are weak, an isolated incident can become a domain, cloud tenant, or production environment compromise. Most privileged access attacks begin with an ordinary foothold: a phishing email, exposed password, vulnerable server, or compromised laptop. From there, the attacker looks for anything that unlocks more access, such as credentials, tokens, active sessions, keys, or weak permissions. The critical shift happens when user access becomes admin access. At that point, the attacker can move laterally, reach higher value systems, and create persistence through backdoors, scheduled tasks, new accounts, or service accounts. This is how impact can escalate quickly, from data theft and ransomware to identity takeover, sabotage, or long-term control. Credential theft is often the first domino in a privileged attack. An attacker does not always need to exploit a server if they can sign in as someone trusted. Passwords are only one target. Hashes, tokens, SSH keys, API keys, browser sessions, and cloud credentials can all act like keys to the environment. Reuse makes the damage spread faster. One exposed credential may open admin tools, databases, cloud accounts, applications, and shared repositories. The risk is even higher when secrets sit in scripts, browsers, tickets, or unmanaged vaults, and when MFA, monitoring, and rotation are weak. Modern credential attacks are built to stay quiet and scale. Password spraying flips brute force around by trying one common password across many users, reducing lockouts while still finding weak accounts. Phishing targets the person directly, stealing passwords, MFA codes, or even session tokens that bypass normal login. MFA fatigue abuses trust in push notifications, pressuring users until one accidental approval succeeds. The highest risk target is any privileged account. If an admin is compromised, the attacker may move directly from stolen identity to control of critical systems. Once an attacker controls an endpoint or server, credentials are often the next target. They search memory for active logons, local stores for saved secrets, cached sessions for Kerberos tickets, and browsers or admin tools for reusable access. Administrative workstations are especially risky because one interactive privileged login can leave tokens or cached material behind. Those credentials can then be reused against servers, Active Directory, or cloud services. The defense is to reduce what can be found: isolate admin sessions, use privileged access workstations, enforce MFA, vault secrets, and limit local admin rights. Exposed credentials often come from normal engineering work, not obvious negligence. A key gets copied into a repository, a CI variable is logged, a script stores a password, or a container image keeps an old environment file. In cloud systems, the blast radius can grow quickly because keys, service principals, managed identities, and metadata endpoints may grant direct access to data or infrastructure. Treat non-human credentials as high-risk assets. Scan continuously. Rotate when exposure is suspected. Enforce least privilege. Use vault-backed injection. And prefer workload identity over long-lived secrets wherever possible. Privilege escalation is the moment ordinary access becomes dangerous. An attacker may start as a standard user, then look for weak service permissions, unpatched software, insecure tasks, or local admin rights to gain control of one machine. From there, they search directories for nested groups, delegated permissions, and weak access control lists that create a path to domain authority. In cloud environments, the same pattern appears through permissive IAM roles, role chaining, service principals, or consent grants. The goal is always the same: climb from limited access to broad administrative control. Escalation often starts with everyday administration drift, not sophisticated malware. A nested group can quietly grant domain-level power. A writable service path or script can let an attacker replace what a privileged account runs. Using the same workstation for email and administration exposes admin sessions to phishing and credential theft. When access reviews are rare, old roles and temporary exceptions become permanent risk. The mental model is simple. Every permission, delegation, and execution path is a trust relationship. If no one owns it, reviews it, and limits it, attackers can turn it into a ladder. After initial access, attackers rarely stop at the first machine. With credentials or elevated rights, they use remote access, admin shares, management tools, directory services, and cloud consoles to move toward higher value targets. Workstations become stepping stones to servers, domain controllers, databases, backups, and cloud control planes. The faster this path is, the bigger the blast radius. Flat networks, shared passwords, unmanaged local admins, and broad trust make movement easier. PAM slows the attacker down by isolating sessions, rotating secrets, brokering privileged access, and removing standing privileges wherever possible. In Windows domains, attackers often do not need the clear text password. They only need something Windows already trusts. Pass the hash reuses a stolen NTLM hash to authenticate as a user. Pass the ticket reuses Kerberos tickets, such as a TGT or service ticket, to reach resources under another identity. Kerberosting works differently. The attacker requests service tickets, takes them offline, and tries to crack the service account password. Defenses focus on limiting useful artifacts through strong and managed service account passwords, tiered admin boundaries, LSASS hardening, and credential guard. Imagine 5 teams using the same domain admin password: IT, support, operations, a contractor, and a vendor. At first, it feels efficient. Then the contractor leaves, the password is reused, and a risky change appears in the logs. Now the investigation hits a wall. The account performed the action, but who was behind the keyboard? PAM fixes this by replacing shared use with named access, controlled checkout, recorded sessions, and automatic rotation after use. Most PAM breakdowns are not dramatic zero-day events. They come from everyday operational drift. A service account keeps the same password for years. A user changes roles, but old admin rights remain. A privileged session runs without recording, so no one can prove what happened. The fix is discipline, not just tooling. Every privileged identity needs an owner, discovery coverage, rotation, and periodic review. Every sensitive session needs monitoring, recording, and alerting. When these controls work together, PAM becomes a continuous operating practice rather than a one-time access cleanup. The big takeaway is that privileged access attacks unfold as chains. A stolen credential can lead to escalation, lateral movement, control failure, and enterprise-wide impact. That is why defenses must limit standing privilege, verify every request, grant access only when needed, and constrain what admins can do. Next, we turn those ideas into access models: least privilege, zero trust, JIT, and JEA.